Hi dear students. So in this section we will discuss the dynamics of rotational motion about a fixed axis. So the work, momentum, all those things in the case of the angular motion or the rotational motion that we will discuss here. First of all, in this table we are having an analogous comparison between the linear motion and as well the rotational motion given. So first of all, just to go through that one, then you will get an idea about what we are going to do. Okay. So the first one, the displacement. In linear displacement, it will be represented as a x. And in the case of the rotational motion, the angular displacement we are considering, that is the angle value will be there as the displacement. So angular displacement will be represented as the theta. Okay. Now linear velocity, the linear velocity value v will be is equal to rate of change of the displacement x. Here in this case of the rotational motion, that will be the angular velocity omega will be is equal to rate of change of the angular displacement theta with respect to the time, that is d theta by dt. Here in this case of linear motion, that was dx by dt, that is v is equal to dx by dt, and here in this case of the angular motion, that is omega is equal to d theta by dt, the angular velocity. Okay. As well, the angular acceleration alpha value will be is equal to, the linear acceleration a will be is equal to dv by dt, and as well there in this case of this angular motion, the angular acceleration alpha will be is equal to d omega by dt. And in the case of the linear motion, the mass, we have to consider the mass, rest mass, and the analog of this rest mass in the case of the rotational motion is actually the inertia, the moment of inertia, I. And force is equal to m into a. So force F is equal to m into a. So instead of m, you have to use the I, and instead of a, you have to use the alpha in the rotational motion. So the force and the analog of force, it is actually the torque. Tau is equal to R cross F, that we have already discussed. So tau is equal to I into alpha. Okay. Now work dW. Work dW is actually FDS, force into the displacement. This is here in this case of instantaneous displacement is given, that is ds. So the work done in the case of the angular motion, that will be tau into d theta, the torque into the angular displacement. Okay, FDS tau d theta. Now the kinetic energy K is equal to mv square by 2. In the case of the angular motion, instead of m you have to use I, instead of v you have to use omega. So the kinetic energy in the case of angular motion will be is equal to 1 by 2 times of I into omega square. Power P is equal to F into V in linear motion. Here in this case of the rotational motion, power P is equal to, instead of F you have to use tau, and instead of V you have to use omega. So tau into omega will be the power. The last one, that is the linear momentum, m into v. So I into omega will be there. That is angular momentum L is equal to I omega. And we have already seen that L is equal to R cross M into V. We have seen that is R cross P is equal to L as well. Another equation in the terms of angular velocity and the moment of inertia, the L can be represented as I into omega. Angular momentum L is equal to I into omega. So some detailed descriptions of the content which we are having in this table, that we will do in this section. Okay. Actually, you have to study, or actually this is the comparison of the linear motion and as well the rotational motion. So if you are studying this one, it will be very helpful for the further exercise problems and as well all other things. Okay, so you can remember the equations, the angular motion, kinematic equation you can remember in such a way. If you are, it will easily you can remember and recall if you are comparing this one with the linear motion. Okay. Now, so in this section we will be considering only the rotational motion about a fixed axis. So two conditions are there. So we will be considering only the torque which are along the direction of the fixed axis. Because if you are considering the torque values which is perpendicular to the or the component of the torque which is perpendicular to the axis, then that torque value will change the direction of the axis. Now we will be considering only the condition, for our simplification we will be considering only a fixed axis. So we are not mentioning, we are not considering the torque, the perpendicular component of the torque, or the component of the torque which is perpendicular to the axis, that we are not considering. Okay. So we need to consider only the force, only those force that lie in plane perpendicular to the axis. Okay, the forces which are lying on the plane which is perpendicular to the axis. That means the force is perpendicular to the axis, in the sense the torque value will be parallel to the axis. Okay. If the if the force is lying on a perpendicular plane, that means that the force value it is perpendicular to the axis. So the torque will be actually the R cross F is the torque value. So torque value will be perpendicular to this force value. That means that will be parallel to the axis. Okay. Actually that torque values we need. Okay. And the force which are parallel to the axis will give torques perpendicular to the axis and need not be taken into the account. So we will not be considering the forces, linear forces which are parallel to the axis. If you are considering such forces, then the torque value will be perpendicular, and that torque can change the position of the axis. So that will be controversial to our consideration. We will be considering a fixed axis only. The fixed axis rotations only we are considering in this section. Okay. And as well we need to consider only those components of the position vectors which are perpendicular to the axis. So the position vectors are also should be perpendicular to the axis. The component of position vectors along the axis will result in torque perpendicular to the axis and need not be taken into the account. So if you are considering the position vectors, position vector in the sense from origin to the particle, the distance or the direction from origin to particle, that is the position vector. So that should not be parallel to that position vector should not be parallel to the axis. That should also be perpendicular to the axis. Then only the component will be perpendicular to, will become perpendicular to the will become parallel to the, that is torque component will become parallel to the axis. Okay, so the force and position vectors both should or both are in a plane which is perpendicular to the axis. Then only the component, that means the vector product of this force and displacement will become parallel to this axis. Okay. Now, work done by a torque. So work done by a torque that we are going to discuss now. So here a cross section of a rigid body rotating about a fixed axis which is taken as it is Z axis. So here X and Y axes are given. So Z axis will be pointing from the screen towards you. Consider like that. So the portion of that body it is rotating about this Z axis. Consider only those forces which lie in a plane perpendicular to the axis. So the force should be in the plane perpendicular to the axis. So the axis that you have considered it is Z axis. So the forces should lie in the plane of XY, X and Y plane. The force should lie in the XY plane. That means on the plane of your screen. That is the XY plane. Okay. Let F1 be one such typical force acting as shown on the particle of the body at point P1. So at P1, the F1 force it is acting and which is perpendicular to the axis of rotation, or we can say the Z axis, Z axis. Hence the torque value will be parallel to the axis. And its line of action is also perpendicular to the axis. Which one? The force. Force F1's line of action is also perpendicular to the axis. Okay. Now, here ds1 is actually as a result of the applied force, the P1, the particle from P1 will move to the point P1 dash. Okay. So P1 to P1 dash a movement it is happening. Okay. Okay. From P1 to P1 dash the movement it is happened. And the displacement there it is was ds1. So using the arc equation, ds1 will be is equal to r1 d theta. r1 d theta, that is the radius. r1 is the radius, d theta is the angular displacement. So the arc length will be r1 d theta. So here it is given, here d theta is the angular displacement of the particle and d theta value it is equal to P1 Cp1 dash. Now we have to find out the work done on the particle. So the work done is actually, if you are considering the linear displacement, that is the linear displacement, if the displacement is very less, this arc will be considered as a straight line. So the ds1 is the displacement. And where the linear force that you have applied it is F1. So the work done here in this case as a will become F1 into ds1. That is the work done. Now, F1 dot ds1. Okay. It is a force dot displacement. Now the angle between the force and the displacement vector, it is phi 1. It is taken as phi 1. Okay. Angle between the force, linear force and displacement, the direction of the displacement, that is F and D. The angle between them it is phi 1. So F1 ds1 phi 1 will be the magnitude of the work done, where ds1 is equal to r1 d theta. F1 ds1 is equal to r1 d theta, and cos phi 1 will be is equal to sine of the alpha 1, where alpha 1 is the angle between the force and the position vector, okay, or the r1 we can say, in the direction of r1, the radius and f1, that is actually the alpha 1. We have taken that one angle as a alpha 1. Okay, the cos of phi 1 will be in this direction. This sine of alpha 1 will be also in the same direction. So cos of alpha 1 will be taken as, or we can consider the cos of alpha 1 as sine alpha 1 for our consideration. Okay, alpha is actually the angle between the f and the r. Okay, so ds1 you are writing, you are substituting this equation here. So f1 r1 d theta sine alpha 1. Now here alpha 1 plus psi 1 will become 90 degree. Okay, alpha 1 plus psi 1 will become 90 degree, this angle. That is one is in the direction of the radius and another one it is in the direction of the tangent. So tangent and the radius always will be normal to each other, or will be perpendicular to each other. So alpha 1 plus psi 1 or the phi 1 will become 90 degree. Okay. So here the effective torque value, if you want to find out the torque value τ1, that is actually Cp cross F1. F1 crosses Cp. Cp is the R value and F1 is the force, linear force. So R cross F. So here the τ1. It is directed along the axis of rotation and it's having a value, having it magnitude as τ1 is equal to r1 f1 sin alpha, where Cp and f1, the angle it is alpha, in between the angle it is alpha, So R cross F, R1 cross F1 is equal to, that is tau 1 value, that is R1, the magnitude it is R1 F1 sine alpha. Okay. So we can write from this, comparing this one, the dw1, this here you have written that one, f1 is equal to r1 f1 r1 d theta sine alpha we have written. So we have seen that tau1 is equal to r1 f1 sine alpha. Okay, sine alpha 1. Okay, so this portion, that is f1 r1 sine alpha, will become tau 1. Okay, so dw1 will become tau 1 and into d theta. So tau 1 into d theta. Here tau is the angular force and d theta is the angular displacement. So if you are comparing this one with the linear work done, the work done is equal to F dot ds. So compare this one with this angular work done. You can see instead of F we are having the F1 ds. If you are considering, then you are having the tau 1, that is the moment of force, and d theta, that is the angular displacement. Here it is linear displacement. So similar only, isn't it? So the angular work done will be the moment of the product of the moment of force, or dot product of the moment of force and the angular displacement. So likewise, if we are having numerous number of forces, like n number of torque values, if you are n number of forces, linear forces, if you are applying on a particular axis in a, as a reason, various number of, that is n number of torque values also will be generated. So tau 1 plus tau 2 plus etc. up to tau n into d theta, the angular displacement, that is the angular work done. In general, the total work done dw is equal to tau, that is the total torque into the displacement. Which displacement? Angular displacement. So it is similar to F dot ds. Okay, work is equal to F dot ds. Now we have to discuss the power. Work we have discussed. Now comes to the power. Power is actually the rate of change of the work done with the rate with respect to the time. So P is equal to dw by dt. In the case of linear motion, you know that the P is equal to F dot V. Okay, P is equal to F dot V. This one it is dot only. Okay, F dot V. So if you are considering the angular motion, the F instead of F, it will be replaced by tau, and the V, it will be replaced by omega. So we are doing that one, the same thing with we can say with the derivation we are doing that one. So P is equal to dw by dt. So tau it is fixed, theta is the value changing, that is d theta by dt will be there, and d theta by dt is actually the omega value. So P is equal to tau into omega. It is similar to the linear force, that is F dot V. The angular power in the case of the angular motion is equal to tau into omega. Okay. So in a perfectly rigid body, there is no internal motion. So there will be no internal motion. So the work done by external torque is therefore not dissipated and goes on to increase the kinetic energy of the body. So the work done will be completely used up for increasing the kinetic energy. So if you are finding out the change in kinetic energy, you can find out the value of the work done. Okay, if you want to find out the how much work it is done per second, if you, that means work per second, it is a work per unit time, it is actually the power. That one also you can find out with the help of this derivation. There is d by dt of I omega square by 2. I omega square by 2 is actually the um, kinetic energy in the case of the rotational motion. That is mv square by 2 replaced by I omega square by 2. So here the omega I is a constant term, so I will be taken outside. Omega is actually a term which is depending upon time. As the time changes, omega can change, omega will change. So the d omega by dt, so d by dt of omega square you have to say. I by 2 will be taken outside, and d by dt of omega square, it is actually 2 omega. And now again we have to find out the d by dt of this omega. Omega square, the omega square we have done. Now for omega it will become d omega by dt. Okay, so 2 omega d omega by dt, and I by 2 will be there. Okay, I by 2 also will be there. So I 2 omega d omega divided by 2 into t. Okay, that is actually the d by dt of I omega square by 2. Here this d omega by dt is actually our alpha. It is a linear rate of change of the angular velocity will become the angular acceleration, so alpha will become d omega by dt. Okay, alpha is equal to d omega by dt. Okay, so d by dt of I omega square by 2, 2 will be cancelled. So I omega square by 2, that is actually the rate of change of the kinetic energy. The rate of change of kinetic energy should be converted into the work done, or the work done will be completely converted into the rate of change of kinetic energy. So rate of change of kinetic energy will be is equal to the work done. Okay. So d by dt of I omega square by 2 will become I into omega into alpha. Okay, I into omega into alpha. That is d by dt of I omega by 2 can be written as the P. The change of that is the change the work done per unit time, or we can say the change in kinetic energy per unit time, that is actually equal to the work done per unit time. So the work done per unit time, it is actually the power will be equal to tau omega, which is equal to I omega alpha. So we are on both sides, we are removing the omega values, so we will obtain tau is equal to I into alpha. Okay, rewrite this one in terms of the linear motion. Tau f is equal to I, instead of I in linear motion, m alpha a. F is equal to ma, that is Newton's force law. F is equal to m into a, Newton's motion's law, and that is actually the tau is equal to I alpha is actually the analog of that of Newton's force law. Tau is equal to I alpha in the rotational motion. Okay, so that we have if you want to find out this, so if it is asked to derive this equation, you have to start from the dw work value. First of all, you have to derive the work, then you have to find out the rate of change of this work value, and from that one again you can explain that in the case of a perfectly rigid body, you have to mention that one. Yes, in the case of a perfectly rigid body, there will be no internal motions, though the work done will be completely converted into or used up for the change in the kinetic energy. So rate of change of kinetic energy you have to find, and that one will be is equal to the power value. So comparing that one, that is the tau will become I alpha, and comparing that one with the f is equal to ma equation, that is tau, instead of tau you have to write f in the case of linear motion, that is I will be replaced by m, and as well alpha will be replaced by a. So that are the analog values. Okay, linear and rotational motion, and then you have to write it. That is tau is equal to I alpha is the analog of Newton's force law in the case of the rotational motion. Okay, so the further portions we will discuss in the coming video section, and as well we will discuss the exercise, the major exercise or important exercise portions we will discuss, and one answer link I will share you. You just go through that link and with the help of the hints you just try to find out the answer and study those things. Okay, and some major equations, so there is indirect questions we will discuss in the class, in the online section we will discuss. Okay, okay then, thank you.